Okay, so let's continue. Let me remind you that if you have a question, please say it on the chat. Please say it out loud. Don't write it on the chat because I won't be able to see it. All right. So today the main goal is to prove the Tom Transversality Theorem. So the theorem that we're going to prove today, it's Tom Transversality Theorem. It's a very general theorem that I stated last time that says the following thing. So let X and Y be manifolds and pick a submanifold of the K-jet space of X and Y. And let TW be the set of functions such that the K-jet of F is transverse to W. Then TW is a residual subset of C infinity. Moreover, if W is closed, then TW is open. Okay, so this second part, remember, we've already proved. It was a proposition earlier. It was a proposition yesterday that we proved that TW is open if the submanifold is a closed subset. But we're going to use this in the proof, so for different W's. Okay, so let's have the proof. And this is going to be a little bit long, so let's get ready. But I think it's, I don't know, I think in a way it's a little, it's easier than the proof that the space of infinity functions is bare. So you just kind of have to look in coordinates. So before I actually write down the proof, I just want to give you the, I want to give you an idea of the proof. So the idea is, you want to say, you want to prove that a set is residual. So what does that mean? It means that it's a countable intersection of open and dense sets. So we're going to basically, the idea is we cover the manifold with subsets that are, we have an open covering, and then that are small. So then we can do something in this small set. We can perturb the function in kind of the small set and show that basically that it's dense if you just allow for little perturbations on a small set. So if you change f just in a little small open set, then you'll be able to find a dense set of transverse functions. Or so where the kth jet is transverse, this kind of slightly stronger transversality question. And then because all the manifolds are second countable, then you can find a countable collection of those. So that's kind of the idea. So let's do that. So first of all, for each point in W, remember W is a submanifold of jets. So for each jet, we're going to choose an open neighborhood of sigma that's sufficiently small, such that we're going to choose this, and we're going to choose open neighborhoods the sigma. Well, let me just write it like this. Sorry, to have better notes, I'm going to choose a neighborhood of sigma. I'm going to choose this is a neighborhood, and I'm going to choose this. Neighborhoods of sigma. Then I'm going to choose a neighborhood of alpha of sigma, so the source of sigma. And I'm going to choose a neighborhood of beta of sigma, respectively. And I'm going to choose charts phi sigma from u sigma to Rn, and psi sigma from v sigma to Rm, such that, so, I choose small enough neighborhoods in these manifolds with the following properties. So I want I want that the closure of this is contained in W and is compact. So, I'm on a finite dimensional manifold, so I can always choose a small enough neighborhood that's compact. I also want to assume that U sigma bar is compact. This is the smallest set of assumptions. I could, basically choose more. And then, sorry, there's no U and V. I really mean this is a chart in X and Y. Then I want to assume that if I take the sources of all of W sigma bar, that this is contained in my domain U sigma, and that beta of W sigma bar is contained in V sigma. So I can choose, W sigma to be small enough with this property because alpha and beta are continuous. Okay? And finally, this is just to make it a little easier. I'm going to suppose that psi sigma is surjective. So, usually a chart, we have the domain of the chart and we have the image. We don't necessarily assume that it's all of the target space, but you can always make it into a little ball and then take a diffeomorphism of the ball into the whole Euclidean space. So you'll see why this is going to be nice to assume. Okay, so I'll assume that the image of the second chart in Y is all of Rn. Okay, so what we're going to do later is, this W sigma is a open covering of W. And therefore, first of all, the transversality condition, if we prove the transversality condition in an open neighborhood for every point, then it's of course true for the whole thing. And then the other thing is that since it's an open covering and the manifold, every manifold by assumption is second countable, we can choose a countable subcovering. Okay, and then basically we can choose a countable collection of sigmas so that we have a covering, and then the TW is going to be the intersection of all of them. Okay, so because of that, for now, we're going to actually concentrate on just one of them. So we're going to let, actually, let me just say that if we say that, this is kind of a definition, that G, a function G, is transverse to W on a set A if G is transverse to W for every X in the preimage of A. Okay, so this is just basically saying if I take another subset in Y, in this case, it's actually going to be contained in W, but it doesn't even have to be contained in W. You just say that it's transverse on A if this condition holds. So, it's kind of the obvious thing. So if it is transverse for all the points that are lying above A. Okay, so so the preimage, a point that is in the image, whose image by G is in A, either it doesn't intersect W, or the transversality condition holds if it's on W. Okay. All right. So then we're going to let T sigma be the set of functions such that the kth jet of f is transverse to W on W sigma bar. Okay? And then what I told you, it's kind of almost obvious that TW is just the intersection of all of the T sigmas for sigma in W. And that's because because W sigma bar is a covering of W. So you can, if it satisfies, if the kth jet of the function is transverse to W on all the W sigma bars, then it's transverse to W everywhere. Okay? And what we're going to say is, because the W sigma bar are covering, then there's a finite number of these sigma i's, these sigmas that, not a finite, a countable number that will be enough. So since W is second countable, there exists a countable covering W sigma I of W for I equals 1 to infinity of W. So TW is the intersection of T sigma I for I equals 1 to infinity. So what we need to show is that these T sigmas are open and dense. Okay? So that's the claim. This sigma is open and dense. Okay. So first of all, let's prove that it's open. And that basically we've already done. That's the proposition that we proved last time. I mean, we proved a slightly different proposition, but it's basically the same. It's the same proof. So the proposition that we proved last time, and I'm going to just slightly modify it, is the following. So let X and Y be manifolds, and W be a submanifold of Y. And let's say that W tilde is a closed subset of W, closed subset in Y. Then the set of functions which are transverse to W on W tilde is open. Okay, so this, it's not exactly what we proved, but it's very similar. And basically you just have to see that we only really need, we can check the transversality condition on a smaller subset, and if that smaller subset is closed, that's what you need for this set to be open, for that sequence to converge. I mean, it was the first step where we really used the fact that W tilde was open, that the W tilde was closed, sorry. Okay, so if we know this proposition, then we just need one more step to get to T sigma. So this is the proposition. So to show that T sigma is open, I'm going to define a T sigma tilde, which is the set of functions G that, because now I don't want my W's in the jet space, not in Y, so I need a slightly adapted proposition. So, I'm going to look at T sigma tilde, which is the set of functions from X with values in the kth jet bundle, such that G is transverse to W on WJ bar. Okay, so by this proposition, this T sigma tilde is open. Okay. So now we want to go from this to the set of smooth functions whose jet is transverse. So we simply use the function j to the k. And so recall that this function that goes from c infinity of xy to c infinity of x jk is continuous. Yes. So T sigma, which is just the inverse image of T sigma tilde, is open. And we're done. Okay, any questions? All right, so now we're going to prove that T sigma is dense. So that's the more interesting part, or the new part, I should say. So how do we prove that a set is dense? Well, we have to prove that, I guess the definition is given an open set. It has to, any open set has to intersect this point. So you take an open set and you have to show that intersects this point, this set. So that's one way. Another way, which is kind of implies this, it always implies this, but in some less bizarre topologies it's equivalent, is to show that there is a sequence converging to any point. So that's what we're going to show. So we're going to let f function, and we're going to construct a sequence Gn such that Gn belongs to T sigma and Gn converges to F in the C infinity topology. Okay? Any questions about this? Okay, so how do we do that? Well, what we're going to do is we're going to perturb the function f by polynomials. So if f was a function that was from Rn to Rm, then we could just simply, without looking at manifolds or anything, we can actually consider if we have we could just perturb f by polynomials, and then if we're lucky enough, we can say, if there are enough polynomials, if the degree is big enough, then we have the transversality condition that we needed for the lemma last time, which was sufficient to show that, for a generic polynomial, for almost every polynomial there, that we get the transversality condition. So that's what we're going to do. So I guess the idea, and now let me write the idea, because then it gets a little, to write things down, and it's a little messy, and we have to use charts, and maybe I don't want you to get lost in the charts, but because it can get a little dizzy from going back and forth between charts and the manifold. But let me explain the idea first. So the idea is to define a map like this, which is basically going to be, the kth jet of some function, j of b, where j of b, or g of b, is a polynomial perturbation of f. And we're going to show that there is a small open ball around the zero polynomial. And these are, if we choose polynomials with degree sufficiently high, so basically polynomials of degree less than or equal to k, we're going to show that we can find a set of parameters such that this phi is actually transverse to anything. In particular, it's transverse to W. I mean, it's going to be actually quite strong. We can build a phi, capital Phi, which is a local diffeomorphism around any point that's on W J bar. So that's on the per image of WJ bar, WJ sigma. Sorry. So yeah, in particular, it'll be transverse to this. So we will have that phi is a local diffeomorphism at every point xb in the preimage of W sigma bar. So we build a map, which is local diffeomorphism in this preimage, and that will mean that, in particular, it has to intersect to intersect W transversely. Okay? So how do you do that? Like I said, if we were in Rn and Rm, you can just basically sum with polynomials. So that would be the map. You just add the polynomials. And that you have to prove that if the degree set, if the polynomials have degree at most k, then this will be a local diffeomorphism. And you can do that. And it's maybe not that surprising because the jet space it's just, if you have Rn and Rm, it is just the x times the polynomials of degree up to k. So that's kind of why it works. But since we're doing things on manifolds and jet spaces, that's we have to do the notation. The notation is a little heavier, and so I'm just warning you. But anyway, before we write down everything, are there any questions about the idea? Okay, so to make sure everything works, so we have to do this in charts. So we have to perturb it in charts, and then we have to glue it to a perturbation on the whole manifold. So to be able to do that, I have to put some bump functions that have, I have to define bump functions that are supported in the charts. So we're going to fix smooth functions. These are bump functions. Row 1, that goes from Rn to 0, 1. And row 2, that goes from Rm to 0, 1. Such that, so I want row 1 to be identically 1 in a neighborhood of the image of alpha of W sigma bar. So, that means, that, yeah, remember that, sigma was a small enough open set in W, and I just want an alpha of sigma and alpha of sigma bar. This is just the sources of these guys, and I also want the support of row 1 to be contained in U sigma. And remember, this is a compact set that's contained in U sigma, so I can always choose a row 1 like that. And again, and similarly, I want the row 2 to be 1 in a neighborhood of psi of beta of W sigma bar, and I want the support of row 2 to be contained. No, sorry, this doesn't make sense. I want the support of row 1 to be contained in phi of U sigma. And the second condition I don't need to require, because remember I assumed that the V of that the image of V sigma was everything, was all of Rn. So the second condition is that, because I guess I just need to just suppose that the support is compact. So let me say that. The support of row 2 is compact. All right. Okay, so I chose my bump functions, and you see why they're going to be important but I think it'll be pretty clear. So now let B be the set of polynomial maps from Rn to Rm, and I'm not assuming that they have zero constants, so they can have constants too, of degree less than or equal to k. Okay, so now I'm going to define my perturbation. So for B, a point in B, I'm going to let GB of x. So this is going to be a perturbation of x, of f. So this will be, let's see if I can write it here. So it's going to be f of x if x is not in U sigma, or f of x is not in V sigma. So outside of U sigma, if the domain is not in U sigma or the image is not in V sigma, then I don't change anything. But if I'm in U sigma and the image is in V sigma, then I define the following things. So let me see. Okay, so I define phi psi of f of x plus. Now I want to write my polynomial. So here's my polynomial. So I'm just perturbing the value of the function by the polynomial. But then I have to use my bump functions so that I actually don't perturb at all when I'm outside of this chart, because I don't know how to, go. If I'm outside of the chart, then I kind of lose control. So this is times. Actually, sorry. Let me do the following. I'm going to change this definition. I don't think this is quite what I want to say. So this is really what I'd like to say. I would really like to just do this, but to make things right, I have to multiply this by phi1 by the bump function applied to phi of x, and then by the second bump function applied to psi of f. And then I get this is a point now in Rm. So now I have to use the chart, the inverse of the chart, to go this is actually well defined. Yeah, that's because I use my trick. So this is what so this is what I do. If x is in U sigma and f of x is in V sigma. And I don't do anything if x is not in U sigma or f of x is not in V sigma. Okay, so that's the definition of GB. And notice that this makes sense because, as I said, the psi is surjective. So this chart takes value everywhere. So I can perturb by a polynomial. I can be taking some value really, really big, but I can still take the inverse, and that's going to fit in V sigma by definition. Okay. I mean, if you didn't want to do that, you could say this, but then you would only allow polynomials that are sufficiently small, and it would be a little harder to write. Okay, so that's my GB. And if you write G, this function, and it's defined by GB of x, it's not very hard. Maybe I should say this is an exercise to show that G is smooth. And the nice thing about this, as we're going to see later, is that if we have a convergence in CK here, that implies a convergence in C infinity, because I'm only changing the derivatives up to order k, because I'm putting polynomials of degree at most k, and that's going to be very important later. Okay, So, and then I can define my function capital phi that I promised into the jet space. That's just the kth jet. So it's, like the kth derivative, or the set of all the derivatives up to k, jk of gb at the point x. And again, using this exercise, because G is smooth, it's not very hard to see that phi is also smooth. Okay. So now my claim is that there exists not the set of all polynomials, but there exists an open set, an open neighborhood of 0, of the polynomial 0, such that phi restricted to this neighborhood, to x times b tilde, is transverse to w on w sigma bar. And in fact, as I told you, we're going to show something much bigger. We're going to show that this phi in this open neighborhood is actually a local diffeomorphism. So, in particular, it's the derivative is surjective, and so it's transverse to anything. Okay, so assuming the claim, now we can prove the result. So assuming the claim, now basically this means that there will exist, so assuming the claim, that means that there is going to exist, assuming the claim, now we can apply the lemma from last time. We can apply the lemma from last class. And remember what the lemma said. It said that if this family of maps was transverse to W, then there exists a sequence in the set of B's such that when you fix the B, you have a transverse map that was dense. So there exists a sequence of BNs in B tilde such that Bn converges to 0, and jk of gbn is transverse basically to W on W sigma 2. That's not exactly what the lemma said. I guess the lemma said that you had to intersect this, to be precise. You had to intersect this with W sigma tilde. And to be even more precise, but I don't really want to write this down, we want to do this on an open set. So maybe you take a small neighborhood around this guy. And then you take a small neighborhood around this guy. And then that's more precise. Okay, but I'm not going to worry about this little neighborhood. As you'll see, I don't need to. Okay, but I guess this is the main point. And then once we have a sequence of polynomials that converges to 0, then this also is going to imply that this GBN converges to F in the C-infinity topology. Okay, so that means I found a sequence of smooth functions converging to F in the C-infinity topology, which are all transverse to W on W sigma bar. So, and this k-jet of this is transverse to W on W sigma bar. And that's what I wanted. So that means that T sigma is dense. Okay, so it remains to show that this claim. So it remains to show that I can choose an open neighborhood of the 0 polynomial so that this map phi is transverse to W. And as I said, I'm going to show it's a local diffeomorphism. So now we have to prove this claim. Okay, any questions so far? No? Okay, so proof of the claim. So now I'm going to let epsilon, I'm going to define epsilon to be 1/2 of the distance between the image of wj bar. So this is a compact set. When I look at, psi of this is a compact set, and I know that the bump function rho 2 is equal to 1 in a neighborhood of this compact set. Okay, so I can look at the distance between this and the set of points where rho 2 is not equal to 1. Okay, so this is the pre-image of 0, 1 by rho 2. Remember, rho 2 was the bump function in Rm. And I defined it to be identically equal to 1 in the neighborhood of this guy. Okay, let me go back so you see what I'm talking about. Where did I define my bump function? Right here. See, I defined it to be equal to 1 in the neighborhood of this guy and to have compact support. So that means I can actually look at this, and this will be a positive number. Okay, because because as I said already, rho 2 is equal to 1 in the neighborhood of this guy. So it's going to be different from 1 in a set that's away from this set. So this has a positive distance. Okay, so this is my epsilon, and I'm going to define b tilde to be the set of polynomials such that the norm of bx is less than epsilon for every x in the support of rho 1. Okay, and this, you can take, I don't know, this is a function from, b is a function from Rn to Rm, all the norms are equivalent. You can just take, I don't know, you just take one of these norms, and then you just fix one of these norms of matrices or something, if you want. Normal functions. Okay, so now we will show, now we pick a point in B. Now we fix AB in B tilde such that phi of xb is in W sigma bar. Now we will show that phi is a local diffeomorphism near xb. Okay? And if it's a local diffeomorphism, as I said, it will be, the derivative will be surjective, and therefore its phi is transverse to anything. Okay. So since we're assuming we're taking a point on W sigma bar, then, so since phi of xb is in W sigma bar, then we have that x is in alpha of sigma W sigma bar, and GB of x is in beta of W sigma bar. Because GB of x is just beta of this guy. Okay, so now we can actually, write down what, so then psi of GB of x, so I'm looking at my expression for GB and I'm applying psi to it to get something in Rm. So recall, where is my expression? Here. So I can use the first line to say, what really GB is at this point. So this is going to be equal, and I'm going to apply psi to it. So now I'm in Rm, and what do I have? I have psi of f of x plus, well, I have rho 1 of phi of x times rho 2. So I have my bump functions. And then I have b. Okay. And then now, what is, now, this guy, the difference between these two, I can look at the norm, how far away from f of x I am using the norm in Rm. Yeah, so if you want, you can use the sup norm here. Well, actually, this is just the norm in Rm. So this really is even. You can take the Euclidean norm if you want. Okay, so this is equal to this, which is going to be less than or equal to the norm of b of phi of x. And this is less than 0, less than epsilon for every x in the support of rho 1. So if I'm close enough, so I am in W sigma bar, and so x is in alpha W sigma bar, which is in the support of rho 1. So this thing holds at x and it holds near x. So by the definition of epsilon, this is true. For every b, I still have that rho. No, sorry, this is true even, this doesn't make sense. Okay, so it's true, that rho 1 and rho 2 are going to be equal to 1 here, because I am on the set of points where rho 1 and rho 2 are 1. So actually, what I know is that, let's leave this expression here because, yeah, I don't quite like it like this, but let's leave it like this, and maybe we'll do something with it. No, let's actually, let me do this. And then we'll see. So anyway, we have this expression for g of b, and for x, this is equal to psi of f of x plus just b of phi of x, because I am on because phi of x and psi of phi of x are in the support of are on the places where rho 1 and rho 2 are equal to 1. So we have just this. And now, basically what we want to do is we want to just look at this inverse map. And it's very simple, because this map, this map here is clearly invertible. You just subtract the polynomial. So, basically, if x prime and b prime is sufficiently close to xb, oh, no, sorry. I actually, I thought I didn't need the calculation, but I do need that to say, yeah, I'm sorry. This is true for x, but because, yeah, because the norm of b is less than epsilon for every x in the support of phi 1. What I want to say is that now this guy, then this phi of gb of x is still a point where row 2 is equal to 1. That's what I wanted to say. So therefore, I have not left the, because I chose this to be to have a support. Yeah, so yeah, because of the choice of epsilon. So that means that this expression here continues to hold in a neighborhood. So then, so phi of GB composed with GB is equal to phi composed with F plus B composed with phi. Well, let me put the X here. In a neighborhood of XB. So it means that for X prime, B prime sufficiently close, to XB, there exists a sigma tilde near sigma such that no, sorry, I want to invert the other guy. So this expression holds in the neighborhood of XB. So now if I look at so if sigma tilde is sufficiently close to sigma, then I still have that alpha of sigma tilde. So I still have that the row 1 and the row 2 are equal to 1. So this expression still holds for we can find, yes. So we can find actually a unique polynomial B tilde so that sigma tilde is the kth jet of psi inverse of f of phi of alpha of x tilde. Boom. 1, 2, 3, 4. 1, 2, 3, 4. Plus B tilde of phi of alpha of x tilde. No, of sigma tilde. I think I don't need this one. Okay. So let me just, I wrote some equations. So let me just say what I'm doing. So because I picked the point that's on this guy. Therefore, row 1 and row 2 are 1. So the expression is just this. And because row 1 and row 2 are 1 in the neighborhood of W sigma bar, the source and the target of that, then if I pick a jet that's sufficiently close to sigma, when I look at the alpha and the beta of this jet, then I will still have row 1 and row 2 be 1. So I can actually just invert this expression. Okay, so if I write something like this, I'm going to have a unique polynomial that's going to give rise to this sigma prime. I can prove this, for example. This is not very hard to see. It's just you can look at this, like if you look at the jet space in charts, you have the polynomials of degree k. So you have the original one for f, and then if you change the derivatives a little bit, then you can find a new polynomial, which is just a difference of these polynomials. So you can think of the b as being sort of the difference b tilde as being the difference of the k, the polynomial. So the polynomial, we had I guess we had a notation for this, but let me write it like this. So if you look at sigma tilde in charts, so B of how do you write this? I don't know. I don't want to write this down, but you can write it down. Basically, what I'm saying is when you look at your original jet, so jk of f, that gives rise to a polynomial when you look at the chart. So, it's f of x plus, so it's the chart of f of x plus all the derivatives looked at in this chart. And then when you take another jet that's sufficiently close to it, then you just have to add this other polynomial. You just have to add the difference of the value of the function and all the kth derivatives, and you get this polynomial b prime. So anyway, this is maybe a writing exercise. So, but anyway, I think that it's pretty clear. And of course, you really need the fact that you're using the space of polynomials up to degree k to be able to match all the first k partial derivatives. Okay, so basically that's the end. So this is a local inverse. So we've constructed a local inverse for every xb in the preimage of W sigma bar. Okay? And therefore phi is transverse to W on W sigma bar. Okay, and again, why is that enough? Let me go back and just remind you that now we use the lemma from last class to say that if the family of maps is transverse to a submanifold, then if you let the parameter vary, then for a dense set of parameters, you're going to have the transversality condition on the function or on the jet of the function. Okay, in this case, the function already has the jet in it. Okay. Anyway, sorry, this was slightly confusing, but not that bad. I think, this is actually not a very hard proof. It's just a little hard to write it down. The notation is kind of heavy. Okay. Any questions? No? Are you still there? Can someone? Yeah. Yes, I heard Mike. Okay, someone typed something on the chat. Can someone say what was typed? Nobody? So people not able to talk? Não. Não? Não o quê? Oi? No more questions. Okay, sem perguntas. Tudo bem. Okay, let's go back. So please don't type, because then I can't see. I have to. I'm in full screen. Eu tô na tela cheia. Se você precisar falar alguma coisa, se você puder falar, desmutar o microfone e falar. Obrigado. Então vamos lá. Então é porque eu tô indo numa velocidade boa. Okay, so let's do the corollary. Maybe I'll write this theorem prime instead of corollary to the proof. the theorem prime is that if I actually want to, if my submanifold is contained in some open set, then I can actually perturb the function without changing what happens outside of this open set. So let X and Y be manifolds, and let's take a submanifold of the jet space. Such that alpha of W bar is contained in U, an open set. Then I can choose a sequence of functions inside of this infinity space, such that the kth jet of Gn is transverse to W, such that Gn converges to F. Oh, and I have to fix a function, a smooth function. And Gn is equal to F outside U. Okay, so I can perturb the function F to attain the transversality that I want, without changing F outside of U. Okay? And the proof of this is very simple. It's just the same proof as before, but you just have to notice that you can pick. The proof is the same as the theorem above, but we have to choose basically, we have to choose all the neighborhoods. We have to choose the support, or the domain of the charts to be contained in U. So we have to choose U sigma inside of this U for every sigma in W above. Okay, so which we can do. So it's very, very simple. So basically, we're only changing the value of F in these U sigmas. So in particular, all the G's, the Gn's will be equal to F outside of U. Okay, that's all. Okay. But I guess it's better to just state the Tom Transversality Theorem without this technical thing, because it's not always necessary. Okay. All right, so now I'm going to actually state the two corollaries of this theorem, which are the, I guess, these are the, I'm going to call these the elementary transversality theorems. So, this is basically the following thing. So if I take two manifolds, and I just look at a submanifold of the target, then the set of functions which are transverse to W is dense in C infinity. And if W is closed, then this set is open. And the second part, which is basically relative transversality, is if you fix a set, you can achieve transversality outside of that set if you give yourself a little wiggle room. So let U1 and U2 be open such that U1 bar is contained in U2, and fix a function F, then there is a sequence Gn of smooth functions such that Gn is transverse to W outside U2, and Gn is equal to F in U1, and Gn converges to F infinity. So if you have U1 and U2, then you can achieve transversality outside of U2 by and at the same time fix F inside of U1. Okay, so I mean, this corollary is basically looking at the case of the theorems for k equals 0, with one more little step. So that's why I think they still deserve a proof. Last time I said, try to prove it by yourselves. I don't think you probably had enough time to do that. So let me just do it for you. So I said it's just basically just the Tom Transversality Theorem and this theorem tilde, theorem prime for k equals 0. But let's write it down. So remember that that the zero jets, this is just x times y, and J0 of f is this basically the graph. The zero jet is x and f of x. So now if we have a w, which is a submanifold of y, then you can look at beta inverse of w, which is going to be just x times w. Okay. Yeah. This is the same beta as usual. I mean, it is a submanifold because it's kind of obvious. It's just a projection. So it's a submersion. So it's transverse to anything. So beta, and it's easy to see what it is. So beta inverse of w is just x times w0. So suppose that J0 of f is transverse to beta inverse of w. So we know there is a dense set of functions that satisfy this condition. So what we're going to see is that this implies the transversality, the simple transversality, that f is transverse to w. Okay. This is almost obvious, but I think it's worth writing down. So first of all, if this is transverse, then either J0f of x doesn't belong to this guy, or it does belong and you have the transversality condition. So if it doesn't belong, that means, that's equivalent to saying that f of x doesn't belong to w. So that means that f is transverse to w at x. Okay, great. And now, if the zero jet of f is in this, and we have the transversality condition, that means that when you look at the tangent space of x times w plus the derivative of J0 of f at x of txx, that will give you the whole tangent space of x times y. Okay, so you see, this is not completely obvious. So this condition is different than the transversality condition, the simple transversality condition on y, which is this one. Okay. But it's easy to obtain this. We just have to apply. We have to apply d beta. So we just basically apply the derivative of the projection at x and f of x. So because this guy is just the x times w, is just the pre-image of w, then when you apply d beta, what you get is t of f of x of y, the tangent space of y. at the point f of x, because it's just a projection. I mean, there are a million ways to see this. And now, when you project the zero jet, the derivative of the zero jet, you just get the derivative of f. So then the second part is really just the f of tx of x. And then here you just project to y. So you get t f of x of y. And that's a transversality condition. So f is transverse to w at x. Okay, so so the set of functions whose zeroth jet is transverse to this is contained in the set of functions such that f is transverse to w. I mean, it's actually an if and only if, but we only really need one direction. So if this set of functions that satisfy this is dense, then this one is also dense. And that's it. And the condition about being open we've already proved. So, okay, so for the second part, for the relative thing, I'm going to define the following thing. So I'm going to let w prime be x times, or I guess pre-image, it's the same thing, beta inverse of alpha of u2 bar. So you just look at, no, sorry, no. I1, hold on. Well, let me write down what I have on my notes. I have x times w minus alpha inverse of u2 bar. Now this is kind of confusing, but I have u1, I have u2, oh, I think I'm flipping them. No, that's right. I want it to be transverse outside of U2, and I want it to be equal outside of in U1. So no, and I think okay. I think this is what I want. I think my notes are wrong. Okay, so I look at x times w, and I remove what's above U2 bar. But U2, remember U2, U1 and U2 are in X. So, when I look at alpha inverse of u2 bar, I really get u2 bar times y. Okay, so that's it. Yeah, that's why, there's this minus sign. Okay, so basically you just look at this w prime, and now you just apply the corollary above, and it's exactly the same thing. So basically, by the theorem prime, we can construct a sequence of functions in infinity such that J0 of Gn is transverse to W prime, and Jn is equal to F on U1. So basically, and hence J0 of G is transverse to X times W off of U2. And as above, by just taking by applying d beta, therefore we get that Gn is transverse to W outside or off of U2. And of course, we chose a sequence. I didn't say that, but sequence such that Gn converges to F in the infinity topology. Okay, so that's it. Okay, so that's the corollary, and that's often how the theorem is applied. The Tom Transversality Theorem. It's often applied just for the case of zero jets, like this. But as you will see in the next class, it can be very useful for the case k equals 1, and in very rare instances, k equals 2. So I have not actually. No, I have once or twice. It's very rare, but sometimes you really use the transversality of k jets. But most of the times it's only 0, 1, and even 2 is pretty rare. Okay. All right. So the next topic that I want to talk about is it's a generalization of jets. It's called multi-jets. So and the theorem for multi-jets will also be quite useful. So let's talk about multi-jets. Okay. So let X and Y be manifolds. And then now we're going to talk about the set of S multi-jets. So for S in N, we're going to define, first of all, what I'm going to call the set of S points in X without repetition. So this is basically the set of X1 up to XS in X to the S, such that Xi is different from Xj for I different from J. Okay, so this is the set of S tuples of points in X without repetition. Okay, so now if we can define alpha S, which is just the function alpha times alpha S times. So this goes from the space of k jets to ds to xs. So this is like the set of S alphas. So we can now define the set of S jets to be alpha S, the pre-image of this set X parentheses S. So what is this set of S K jets? So this is basically the set of jets with with S base points, but I want them all to be all different. So basically, you pick S different points on X, and you pick all the derivatives of a function up to K. That's what this multi-jet really is. Okay, so this is a subset of S, of the set of k jets to the S. And it's open with the product topology. Okay, so it's an open, this is an open manifold. I mean, it's open, so it's a manifold. Let me just say it like this. So JS, okay. It's a manifold. Okay. I mean, it's open because we're taking the pre-image of an open set. Okay. And then now, what is nice is, given a function, you can look at the kth, the sk jet of the function. So, given a smooth function, this gives rise to the sk jet of the function, which is a map from the set of S distinct pair, S tuples of X without repetition into the k-jet space, the sk-jet space. So basically, if you take S different points in X, then you can look at the images and all the first k derivatives for all these S points. That's what the jet map is. So I can write it like this. So what is the JK S of F for x1 up to xs? That's just the kth jet of F for the point x1 up to the kth jet of F at the point xs. Okay, so that's the multi-jet. And then now I'm going to state the theorem of the Tom Transversality Theorem for multi-jets. So this is Tom Transversality for multi-jets. So it says the following thing. So let X and Y be manifolds, and pick a submanifold of the space of multi-jets. And let TW be the set of functions such that the kth, the sk multi-jet of F is transverse to W. Then TW is residual. Moreover, if W is compact, then TW is open. Okay? And you should notice that there is a difference between the first, it looks very similar to the Tom Transversality Theorem for jets, but there is one little thing, which is this condition of being compact, which is stronger than being closed. And you might ask me, so why do you have this condition? And the problem is that it has to do with the fact that, when you're closed here, that doesn't mean, it definitely doesn't mean that you're compact, but something that's really bizarre can happen, which is you can take a sequence of jets of multi-jets, such that the base points are converging to each other, or so that, in the limit, you have two base points that are collapsing. And then, if that happens, then you're no longer in the space of multi-jets. And that's a problem. And that's why we require that W is compact. If you're really careful, you can write a condition that basically means that this doesn't happen, but you can have non-compactness sort of towards infinity. Like you could have the jets going far away from each other, provided that the base points are far from each other. So I think what you really need to I don't know. If you want, think about the specific condition, and I think it's also very helpful to think about an example, a counterexample to this. Like think about a W that is closed in the topology of the set, but such that TW is not open. I think that's a very, very interesting thing to think about. Anyway, this proof of this is very similar to the proof of the other one, but now you have to be careful because you have several points at the same time. So you just have to adapt the other proof, but now you have a little ball around each point. So I'm going to leave this proof as exercise. I actually think it's very nice if you can try to prove this theorem without looking at a book, at anything. I think it's not super easy, but it really will solidify your understanding of the other theorem, the transversality theorem for normal jets. And of course, it'll solidify the understanding of the definition of multi-jets. All right. Are there any questions about this? No? Okay. So since we've had, a lot of, it's been kind of back to back, and this material is kind of hard to digest, I'm gonna stop here for now, and we'll continue in the next lecture. Alguma pergunta? Comentário?
Não.
Não. Tá bom, então. Eu vou salvar isso daqui e vou colocar lá no Google Classroom. Tá? Que aí eu parei um pouquinho antes, a gente está com bastante material, está indo num ritmo bom, e eu acho que a gente não precisa correr também. E para vocês conseguirem digerir também para a próxima aula, que é 1 hora. Então, 1 hora a gente vai continuar a discussão e vai falar sobre aplicações desse teorema. E aí a gente vai começar a ficar um pouco menos técnico e mais colocar a mão na massa mesmo. Tá bom? Então
Beleza.
Tá. Até daqui a pouco.
Até.
Valeu. Tchau.
Tchau, tchau.